Hello everyone watching this video. We are Group 1 Refactory Academy and this is Cohort 3. With me, I'm with Nazziwa Rhoda, Nameeru Bronah and Akampa Godfrey. Today we are presenting our final project, predicting 10-year cardiovascular events using machine learning and deep learning, a heart attack or a stroke model. And basically all our model notebooks and the model deployment are publicly available on the link that is here in a blue color. So when you tap on it, immediately it will take you to all our work, all of our project. So basically this project uses machine learning to support early identification of people at risk of cardiovascular complications. So basically, here we are trying to show our team contribution on this project, whereby Rhoda handled the full exploratory data analysis, and Brunner built and compared classical machine learning models, and I myself, Godfrey, literally built the deep learning modules. And also, when we reach on the model deployment, we all participated on that by choosing the best model, and we saved it via the Streamlit, and we uploaded it on the live web for the clients, as we shall see at the end of this video. Then lastly, all of us together, we also summarized some of the best performing model, the recommendations, and the future work. So when we talk about our project, basically research shows that cardiovascular diseases remain the #1 cause of death globally, almost reaching to 20 million deaths per year. And out of that, 85% of those heart attacks and strokes is the core problem, and that is from WHO 2024. So basically, our greatest burden in Uganda, particularly, and also in the other low and middle income countries, CVD, or what we can call cardiovascular diseases, cause about 10% of premature death between 30s and 70s, as it has been justified by this project of ours. And basically the traditional risk scores like the Fremling and QR risk, as currently where we have the QR risk to struggle with complex interaction between the lifestyle, clinical, and demographic factors. And that is exactly the gap we wanted to cross, or we investigate crossing with our machine learning module. So excuse me, our main goal was to build an accurate deployable ML module that predicts whether a person will suffer a heart attack or a stroke in the 10 years period, so that the preventive care can start early, especially in the resource limited settings like Uganda. And some of our specific objectives, we had 4 of them, of which one has been talked about in the goal, where we aim to predict whether a person will experience a heart attack or stroke within 10 years time. Also, we aim to identify the most relevant demographic, clinical, and lifestyle predictors associated with 10-year cardiovascular risks. And basically, this will enable us, team, and also the healthcare team to recommend based on a data-driven decision. Then the second last is to develop and evaluate classical machine learning models, whereby in this video we shall look at the logistic regression, the random forest, and the k-nearest neighbor classifier for the CVD risk prediction. And when I talk about CVD, as we shall see in most cases, I will be referring to the cardiovascular disease risk prediction. And lastly is to design and train a neural network capable for capturing complex and nonlinear risk patterns in our model. When I go to the data description, as you can see, we worked with a publicly available data of 100,000 patient records from Zenodo, and basically it is a as you can see, our problem is a supervised learning binary classification problem. And when you look on the target vector, which is Y, and that is a heart attack or a stroke occurred, with 0 representing no event and 1 representing an event occurring. So with only 15 meaningful features covering the patient identifier, demographic, anthropometric, then clinical lifestyle risk, clinical measurements, family history for and comorbidity variables, all adding up to 15 meaningful features. These will help us to predict our model. And why basically we chose it as a binary classification. This is justified with an outcome that allows the model to distinguish whether or not a person will experience a heart attack or a stroke within the 10 years. And that is a class of predicting a class of 0 and 1. And hence, it is a binary classification. When we move forward to the exploratory data analysis, the EDA, or what we can call the exploratory data analysis, revealed some of the critical things that we can talk about. As we can observe in the descriptive summaries features, the issues we tackled was duplicate rows, missing values, the target distribution, and also we display the findings and also the actions taken. But as you can see, the highlight we got is that severe class imbalance of a 14:1 negative to positive ratio appeared. And this informed us that focusing on Achilles alone will be misleading. Hence, we prioritize utilizing specialized algorithms, evaluation matrices, and resampling techniques, for example, the SMOTIC on the minority class, or what we can call the yes event, to ensure that the model reliably identify high-risk patients, which is our primary goal of preventing the cardiovascular events. Why we didn't use some of the resampling techniques, for example, the oversampling, basically those ones, they do what we can call a duplicate of the majority class, whereas the SMOT uses a KNN classifier embedded in it, which helps us really to resample properly than making the duplicates, which can lead to overfitting or underfitting, something of that sort. So as you can see on the side of univariate analysis, I will talk about only age, and then the other will be talked about in the notebook as we shall explore it further. But age, basically, as you can see, similar to the body mass index and the systolic blood pressure, all reveal they are normal in distribution when we see the bell-shaped curves. But for age, as I've said, it contains information of 100,000 participants, and the age ranged from 18 to 79. And basically, that interquartile range suggests that the majority of the patients fall within the adulthood to the late middle age. And furthermore, on exploratory data analysis, we uncovered some of the findings with bivariate analysis, as you can see in the statistical tests and the clinical patterns insights. Some of the clinical questions that we uncovered are shown here. Okay, and the results, or what we can really highlight from that, is that age, systolic blood pressure, and BMI, or what we can call the body mass index, all confirmed to be factors that play a major role in predicting cardiovascular disease, or the risks, sorry, for that case. Whereas for gender, it also showed an association between the 10-year CVD event, whereby men experience significantly more heart attacks and strokes than women, with an event nearly 50% higher. Whereas on the other hand, for the smoking versus the events, smoking did not appear to influence the likelihood of experiencing a heart attack or stroke based on the statistical tests. And as we are all aware that smoking majorly affects the respiratory than the cardiovascular system. For the multivariate analysis, we created a new variable called the comorbidities. Basically, this was summing up the raw patients whereby they had responded a yes on all the three categories of the questions, whether a patient simultaneously uh, experienced these three diseases, whereby we have the kidney, we have the atrial fibrillation, then also the diabetes. So our analysis revealed a clear dose response relationship. That is to imply that as the number of comorbidities increase, the proportion of patients experiencing the CVD events also increase sharply. And this demonstrated that the CVD risk, as you can observe on our orange scale, it accelerates with multiple chronic conditions, reflecting a cumulative burden of the disease, and vice versa. So what does this imply? This implies that the patients with multiple comorbidities or some of the diseases which contribute to the CVD risk simultaneously are substantially at a higher risk, highlighting the importance of the integrated care and early intervention. On the machine learning and modeling, we trained three models with a clean pipeline, that is stratified splint and processing and smart, and then the model. And of those models included the logistic regression, not limited to random forest, and also KNN classifier. So as I've talked of the SMOTI, it was applied to collect the class imbalance and some of the various matrices that we used to evaluate our model included the recall, included the precision, included the F1, and also the confusion matrices, which will be displayed in the notebook, as we shall see. So below some are the critical steps that we took for us to avoid the target and the train test contamination. So as you can see on the other side, these are some of the results that we got from the machine learning model after a long period of training. So as you can see from this classification algorithm performance with almost 18,508 holdout tests, the logistic regression model captures 80% of the true events, raising only 18% of the false alarms, and it balances between catching the cases and avoiding false positives at 29% and with an accuracy of 72%. So for KNN classifier, it captures 65% of the true events, raises 16% of the false alarms, and it had an accuracy of 72%. Random forest, it had an accuracy of 87, it attained an accuracy of 87%, but the captured true events were 25%, and it raised an alarm of 20%. So therefore, what does this mean? This implies that logistic regression was selected the best model, as it identified 8 out of 10 patients who will suffer a heart stroke in the next 10 years, hence an ideal clinical excellence for the population level screening and early risk detection in the resource-limited countries like Uganda. Why we didn't choose the random forest? Accuracy alone was misleading from the class imbalance that we saw from the EDA. Excuse me. What we are seeing on the screen right now is the winning model, which is the logistic regression model, and basically, the first part is the pipeline, whereby the numerical variables or features were handled with the simple imputer and standard scalar, and also the categoricals, whereby in most cases we had the binaries of zeros and one, or yes or no, were handled with one hot encoding, and those that remained were passed through. Then we also apply the SMOTI and then the logistic regression. What you see below is a confusion matrix. And this confusion matrix implies that out of, as you can see here in the orange box, out of 18,584 holdout test cases, the model collectively identifies 12,343 high-risk patients who will suffer a CVD event, whereas the 246 imply that the module misses only the 246 patients. On the other hand, the 1,058, it implies it collectively ruled out the low risk patients. And lastly, with the 4,000, our model, it implies that our model along flagged the members, along flagged these members. Okay. For the deep learning approach, as you can see, we explored deep learning to see if a neural network could capture more complex patterns. And as you can see on the next screen, is that even after extensive tuning, which included the deep layers, which included neurons, early stopping, class weighting, the dropouts, among others, the neural network approach failed to outperform the logistic regression model on critical minority class matrices, as we can come back here on the comparison of the baseline and evidence-based case scenario comparison. Only the recall remained dissonant with 87%, but precision stayed as low, and also the F1 score stayed as low. Then from that, we deployed our model, which is the logistic regression, using the Streamlight and the live web arm. As you can see on this link, we had the local host, the network host, and also the deployed link. So basically, if I may share the screen after this video, you can really appreciate that some of the cases were discovered into that model. Upon our study, we concluded that the classical machine learning logistic regression performed exceptionally well, and the majority of the participants fall within the early adulthood to late middle age, that is 18 to 79 years. Also, we concluded that age, SBP or systolic blood pressure, and the body mass index, and also gender, which I think I forgot to include here, confirm to be the factors that play a major role in predicting cardiovascular risks. On the other hand, men experience significantly more heart attacks and stroke than women, with an event rate of nearly 50% higher. And also, smoking does not appear to influence the likelihood of experiencing a heart attack or stroke. And finally, the patients with multiple comorbidities, as we have said, comorbidities being a situation where a patient is experiencing simultaneous number of diseases that contribute or that affect that contribute to the CVD risk event. So patients with multiple comorbidities such as the kidney disease, the atrial fibrillation, and diabetes are substantially higher risk of experiencing a CVD event. And some of the recommendations that we had to put on paper One was to adopt a logistic regression as preferred predictive model for the early screening, and also was to prioritize high groups, for example, the older groups, the hypertensive groups, the patients with CVDs or the diabetes for the targeted prevention programs. We also laid out a recommendation of implementing community-based blood pressure and BMI monitoring, given the strong predictive values they had. Then when we talk about gender, which we also saw as a point that was contributing to the CVD events, sex-specific prevention strategies were also recommended to address the disproportionately higher risk among men. Then the last recommendation that we had to put down was to integrate machine learning screening tools into the routine clinical care, especially in resource-limited settings to support the early detection and reduce the long-term CVD burden. And from all this, when we look at countries like China, we look at countries like United States, those high level class countries, they put much effort in healthcare, like in preventing some of these burdens as early as possible, because this limits the time of a person, or what we can call the workforce, that that it should be spending in treating than it should be working and then resting, and hence an increase in economic growth and also the well-being of the population. And the feature works that we also had was deep learning model expansion should also be put at hand, and the model deployment. This can be looked at an angle of putting it maybe on a Ministry of Health website even when you don't have the data such that any person can access it. Then also the feature engineering. Here we implied that we could explore more additional clinical variables that would improve the model sensitivity. For example, the ECG features, the lipid profiles, and lifestyle metrics for the clinical part. Who might really understand that part? And also we would also look at the longitudinal validation. Here we apply the model to the feature datasets or the real world cohorts to validate the fairness and clinical applicability. Then also for the explainability, to enhance the transparency and support clinical trust, and most importantly, decision making. So if you could allow me, I would share how our model really is working on Streamlight with only 3 case-based scenarios. So as it loads, basically this is our model, and when I can set it to default with all these. So this is our model, basically, as you can see, and these are the developers, as you can see, whom we explained at the beginning. So it has a welcoming header. We'll come back to check on your health status, and prediction is ready. So here we prompt a client who is handling it to enter the details of the patients with age, gender, systolic blood pressure, the body mass index, and also these questions of whether you're a smoker, the diabetes, the hypertension, and whether your family history had a CVD, yes or no. So when I can set it to default, and when I predict, you will say that we are only at 9.57 risk probability. And this implies that there is a low risk and unlikely to experience a cardiovascular event in the next 10 years. So the first case scenario is that when you receive a patient who is at 40 years and then their systolic blood pressure is set at 1 and also the body mass is set at maybe at 25, when we predict for that, that will be a 27.7% still error risk. But one of the predictors was gender. So when I change here and this is a female, I expect this probability percent to increase from 27 to sorry, to reduce, okay? Because in our analysis, we literally identified that males are more likely to get this CVD than women. So you see here there was a male, and when I changed and I put female, it literally dropped by that percentage. So another case I would talk about was the comorbidities, where a patient is experiencing more than two diseases simultaneously. So when we choose atrial fibrillation, we choose chronic diseases, and he says that she says that basically they have a family history of a CVD, then she has ever treated the hypertension, then the diabetes is present. So when we predict that, you can see that almost 54% of the risk probability has been revealed from that. Then another point is that we included the smoker. So even if it is smoker or not, we shall exactly retain our percentage, which is 54%, as you can literally see. So basically, this implies that even if you're a smoker, although the client needed that to appear, being a smoker does not really attribute to your what? To your case. So the same thing when I change to male, we expect this probability risks to increase by a certain percentage, which is 67.28%. So basically, that is how our model works. And as you can see, this is the link that it has been deployed. And I also shared some of the links that are the localhost and then the HTTP localhosts. So allow me take you to the area where we coded, and then I can highlight simple stuff. Then everything will be just found at our GitHub. So this is EDA, where we did a data inspection and cleaning. We imported our most important libraries. We loaded our data, and after loading our data, we had to do an information summary to check to just inspect what are the missing values, are our data types, some are relevant to our data dictionary, and we also checked on that. So as we saw in the presentation, we checked for the duplicates, we checked for the missing values, and as you can see, this is how we captured our missing values with the body mass index at 25%, and also the others also explained. So how we filled out or how we handled our missing values, we first literally consulted from the density plots. How are these? Because they were numerical, and for that case, the density plot can literally help us to identify which imputation strategy that we can use, So as you can see, the blood pressure was normally distributed. The body mass index was also normally distributed, unlike for this, which was not normally distributed. So it implied that for the two, we imputed using the mean, and this one we used the median, relating to this density plot. Okay. The next part we did was to do a univariate analysis, and from this univariate analysis, this is how we interpreted age by using a method of dot describe, and then we transposed, and basically this visualization of age, which is the box plot, it literally gives us a bell shaped, which implies that age is normally distributed for that case. When we look at the visualization for the categorical, sorry, this class was literally greater than the yes class. This case is mostly in these areas. We shouldn't be surprised of that because 90% of the population right in Uganda, although they are not affecting with this, but the little percentage that is affected with it, it is literally affected severely. So the bivariate analysis, we literally uh, uh, explored some of the clinical factors such as the age, BMI, systolic blood pressure, and how they related to a 10-year CVD outcomes. As you can see, there are some of the questions that we did not put in our presentation, but as you go through this, you will literally see what we use. But mostly, especially, we used non-parametric methods, for example, the Mann-Whitney test, and also the chi-square, where we had a comparison of the numeric and then the categoricals. So as you can see, this was the age versus the event where the p-value was less than 0.05, and this implied that age uh, age, basically the age between the people who had a heart stroke and those who did not statistically was statistically significant. And this implied that age is strongly associated with the 10-year CVD events where older individuals in the dataset are more likely to experience a heart disease. As we are aware, when a person grows, these risks are literally closer to his or her dose. And same as for SBP, same as for BMI, uh, same as for BMI, but literally for BMI, this is how we visualized it using the violin. And violin also shows us how it is well distributed. As you can see, no, it is normally distributed where uh, this ring is in the middle and this is just below this. Okay, so that is also another way on how we can visualize a categorical variable using uh, the violin. Uh, um, and and the most important case was uh, between the gender and the event. And as you can see here is a cointelligence table. And before that, we saw a p-value which is less than 0.05, meaning that gender is associated with CVD events. Okay, and how we got the 50% is basically from this co-intelligence table, whereby females were at approximate of 5.26% and males were at 7.96%, and men had a substantially higher event rate than the women, which is about 1.5 times higher. And also, the why we did not include smoking, although it is in our model, it is not making any change. This is the reason. So the relationship of whether a person is a smoker or not with the event, it had a p-value which is greater than 0.05, and literally this implies that smoking does not appear to influence the likelihood of experiencing a heart or stroke based on the statistical analysis that we have seen. And then the multivariate analysis, a lot of things were covered, which I will not cover in this video, but the moment you tap on the link, slowly by slowly, you will understand. And where there is that is and where there is uh, every detailed information. Okay, but most importantly, I will talk about the comorbidities and how we generated that variable, and basically how we came up with that analysis. So comorbidities, we basically created a list of these three diseases, uh, which were a question of whether or not, which is a yes or no, and that is a category. And we applied the lambda, and this lambda helps us to do a simultaneous calculation, or basically it is used in calculus, but this also helped us to sum up the patient row-wise who said yes to the three of the above listed chronic diseases. And it is from that count that we stored in the NAM comorbidities, and we used a method of dot group by, and we normalized it, and basically this unstack just gives us this nice, beautiful visual of this table. And it is from that that we use the bar plot to plot this number of comorbidities with the proportion of participants. And this is how the table looks like. So you will observe that, excuse me, comorbidities at 0, which is at 3.9 events, and one is at 16, and two comorbidities is at 29.47, and also three comorbidities is at 45% events. And basically, this demonstrates that CVD risk accelerates with multiple chronic conditions, reflecting a cumulative burden. Um, and and finally, this graph implies that as a patient, excuse me, as a patient experiences more and more and more diseases simultaneously, the risk of experiencing a CVD event also increases as we can see from this, at 45%. So from the machine learning module, basically what we expect from here is to build and evaluate classification matrices to predict the likelihood of a 10-year cardiovascular event using some of the factors that we prior listed. So some of the machine learning techniques included the logistic regression, random forest, and the k-nearest neighbors. So we had to import relevant libraries, most for visualization, then the machine learning, then the algorithm, then also handling the imbalancing. Of course, we chose this as we also really tried to handle the random oversampling and also the balanced bagging classifier. We loaded the data. After loading the data, we did some high level inspection, as you can see. Okay, I'm trying to rush through this because I know some of these things were covered in the previous part. Uh, but the most important here, we can observe that we did a target variable analysis where we found out that um, there was a high class imbalance, and where we concluded that we would overcome this by using resampling method, specified algorithm methods, and also alternative evaluation matrices, as we shall see. So we had to separate our X features and also Y features, and also from that case, we had to split our data. Okay. And if we can see from this point, we just deleted those which were not contributing to our model, and we had to split our data. After splitting our data, the train testing was at 80% and the test was at 20%. And also we used the feature transformation using the pipeline package. So we handled numerical with the mean. We also scaled them. Then for categorical, since we had the binary case, we only used one hot encoding, and we combined our transformer with using the column transformer. and we started to evaluate our models. So as you can see from the logistic regression, this is how the pipeline looks like. And basically, this is how it really performed using the classification report and the confusion matrix. Furthermore, for KNN classifier, we did some parameter tunings, hyperparameter tunings, but this was our baseline, okay, with KNN classifiers, and this was the classification report and the KNN confusion matrix. Due to time, I'll just bypass small by small, but I'll create another video where we shall be explaining each part by each part. So after parameter tuning, we chose our optimal K to be at 15, or someone would have chosen at 10. So anywhere where this elbow bends, okay? So after that, you see that the recall increased to 65%, and also the accuracy increased to 72%. Then from the random forest, also as you can see the pipeline that was used, also the accuracy was at 87%, but it was really performing poorly on the ES class. And basically that is how we performed our machine learning model. Then for deep learning, the aim for deep learning was to see whether we can capture some of the nonlinear that were not captured in the machine learning modules. So the first step was literally to learn on how we can plot our evaluation uh, models, and of course the deep learning also, um, I think for the period of time, we can just refer to the link. I will just talk about on how we deployed our model, and from that we shall end this part. So how we deployed our model, this is we first saved our model. Let me just on this side. So we saved our model with the with um, with the pickle. You need to import this pickle, and then you save our model using the with open logistic regression model.pickle, and then the WB or write binary as if. And from that, we had to load our model. It's still using the same name, the logistic regression model, and this is how we read our names. Okay, sorry, we created our model. So we had the page title, we had the title, we had the markdown, and from the markdown, we used the st.form and st.submit to capture those columns that you are seeing, where column 1 and column 2 included gender, age, historic blood pressure, BMI. Then column 2 included whether you're not a smoker, diabetes. Also, these were also captured, and also column 3. So this is a function whereby if submitted, all these would be encoded with the dictionary. And from there, we calculated the probability of the predict probability of the class, okay, using the method of the predict probability, and we are capturing that probability from the data that we have captured from the user. And finally, this is how our display will be looking like, whereby if the risk is at 0, we just tell the user that there is a low risk and unlikely to experience a cardiovascular event in the 10-year, unless elsewise that is a high risk. Okay, and this is how we are trying to modify maybe our model to look like, with the subheader, with the metrics, and then with those balloons which we are seeing, and also the markdown, whereby with a low risk you receive a green font style text, and when it is really high you receive a red font style font style text. I want to thank you for your attention, and we are happy to take maybe any questions in the comments, such that we can literally modify our code as we are trying to prevent these silent killer diseases. Thank you so much. This was Group 1.